Welcome to the session on modelling in mechanics. In this unit, we will be looking at key concepts through review exercises. The objectives for this session are to review previous topics through exercises, namely factorise quadratic equations using the quadratic formula and otherwise, and convert kilometres per hour to centimetres per second, and grams per centimetre cubed to kilograms per metre cubed. We will also look at converting large and small numbers to standard form and use trigonometry to find missing sides or angles. Pause the video and have a go at these review exercises. When you are ready to view the solutions, press play. Before we look at the first exercise, let's have a quick overview of the steps for factorisation. So firstly, we write the equation as ax squared plus bx plus c equals 0, then factorise the left-hand side, and finally let each factor equal 0 and solve. So let's have a go at the first exercise. Solve x squared equals 25. This is equivalent to x squared minus 25 equals 0. We've put all the x's and all the constants on one side, as required by the first step. Next, we factorise the left-hand side to give x plus 5 times x minus 5, and of course that equals 0. Some quadratics are easier to factorise than others, and you may have spotted the x squared minus 25 pattern. So x squared minus 25, of course, equals x squared minus 5 squared. If you do find something more challenging, then there is a simpler way, or there is another way of solving these quadratics. However, for the moment, let's go for the simple ones. So how have we factorised the left-hand side? We have x squared here and minus 25 here. And of course the x times 5 and the minus 5 times x cancel out. So therefore we now let each factor equal 0 and then solve. So either x equals minus 5 or x equals plus 5. Now for exercise B. Solve 5x squared plus 2x minus 3 equals 0. Of course, this is already in the format ax squared plus bx plus c equals 0, so we don't need to change it around at all. Next, we factorise the left-hand side. This time we're going to use a slightly different method. We're going to find two factors, ac, which add up to b. So of course, a times c equals 5 times minus 3, which is minus 15. From here, and we need to find two factors which add up to b equals 2 from here. And the two factors we're looking at are 5 and minus 3, since 5 times minus 3 equals minus 15, and 5 plus minus 3 equals 2. And so 5x squared plus 2x minus 3 can be rewritten as 5x squared plus 5x minus 3x minus 3. And then factorising the two parts of this expression gives us 5x times x plus 1 minus 3 times x plus 1. And of course we can factor out the x plus 1 as shown here, and 5x minus 3 goes here. So of course we've factorised our expression, and now we can let each factor equal 0 and then solve. So either we have that x equals 3/5, or x equals minus 1, when 5x squared plus 2x minus 3 equals 0. And now for part C. Solve x plus 3 all squared equals 13. Sometimes it is easier to solve without factorising. Perhaps you can spot why in this example. Suppose we square root both sides. Then we have x plus 3 equals plus or minus square root of 13. Notice here it's simple to square root x plus 3 all squared because it simply becomes x plus 3. And of course 13 square rooted is plus or minus square root of 13. And then we can solve. So either x plus 3 equals root 13 or x plus 3 equals minus root 13. Which gives us x equals root 13 minus 3 or x equals minus root 13 minus 3. And this implies that x equals 0.606 to 3 significant figures, or x equals minus 6.61 to 3 significant figures. And now for review exercise 1D. You may recall we mentioned that if a quadratic is difficult to solve, then we can use another method. And of course that other method is solving using the quadratic formula, which is shown on your screen. So if we have ax squared plus bx plus c equals 0, with a, b and c being real numbers and a not equal to 0, then we have that x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So now let's have a look at review exercise 1D. We have 2x squared minus 9x minus 1 equals 0. So let's solve this. We can find x by plugging into the quadratic formula. We plug b in here and here as shown. We plug a and c here and here as shown, so a equals 2 and c equals minus 1. And we plug in 2a as shown here, so we have 2 times 2 because a equals 2. And then we tidy up, so we have x equals 9 plus or minus root 89 all over 4. And this gives us that x equals either 9 plus root 89 all over 4 or 9 minus root 89 all over 4. Which gives us x equals 4.608 or x equals minus 0.1085. The next exercise requires us to convert 60 kilometers per hour to centimeters per second. So how do we convert units? In this particular example, how do we convert kilometers per hour to centimeters per second? Let's first look at kilometers per hour to meters per hour. We're going to break this down gradually and we'll deal with the seconds later. So if we're converting from kilometers to meters, how do we do this? Of course, we multiply by 1000 because 1000 meters equals 1 kilometer. Then, if we're converting to centimeters per hour, then we multiply the meters by 100 because 100 centimeters equals 1 meter. So overall, in order to convert from kilometers per hour to centimeters per hour, we times by 100,000. Because it's the first 1,000 and then the 100 multiplied by each other. How about converting centimeters per hour to centimeters per minute? Now, since there are 60 minutes in 1 hour, then we divide by 60. And when we're converting from centimeters per minute to centimeters per second, we divide by 60 again because there are 60 seconds in 1 minute. So the overall effect is that we're dividing by 3,600. And here's a summary of the key points. We can now apply this to our example. So first, let's convert from kilometers to centimeters, because that's part of the question. And then we convert from per hour to per second. So first we multiply by 100,000 in order to convert the kilometers to centimeters, and then we divide by 3,600 in order to convert from per hour to per second. So essentially we multiply by 100,000 divided by 3,600, which is equal to 1,000 over 36. And so for our exercise, we multiply 60 kilometers per hour by 1,000 over 36. To give this expression here, 1,000 over 36 times 60. Which equals 10,000 over 6 centimeters per second. And this gives us 1,666 2/3 centimeters per second. And now for exercise 2b. We're required to convert 7 grams per centimeter cubed to kilograms per meter cubed. So we're going to convert grams per centimeter cubed to kilograms per meter cubed. Again, let's break this down. Let's go from grams per centimeter cubed to kilograms per centimeter cubed. So we ignore the meters bit for the moment. And in order to go from grams to kilograms, we multiply by 0.001 because 1 gram equals 0.001 kilogram. And now let's look at what we have to do if we go from kilograms per centimeter cubed to kilograms per meter cubed. So we're focusing on the per centimeter cubed to per meter cubed bit, and we're leaving the beginning bit as it is. So for this we need to multiply by 0.01 to the -3. And of course this is because 1 centimeter equals 0.01 meters. And 0.01 to the power -3 is of course 1 million. And now for the final part. In order to go from grams per centimetre cubed to kilograms per metre cubed, we put these two parts together and we multiply by 0.001 from the first part times 1 million from the second part, which equals 1000. And so, for our exercise, in order to convert 7 grams per centimetre cubed to kilograms per metre cubed, we simply multiply 7 grams per centimetre cubed by 1000. As shown here, to give 1000 times 7 kilograms per metre cubed, which is of course 7,000 kilograms per metre cubed. And now for review exercise 3. We are required to write two numbers in standard form for part A and for part B. Recall that standard form is a way of writing really large or very small numbers, and it follows the format A times 10 to the power n. So let's solve part A first. We're required to write 8,450,000 in standard form. We can rewrite this as 8.45 times 10 to the power 6, because we've moved the decimal place 6 places to the left. And now for part B. We are required to write 0.002708 in standard form. So therefore we have that 0.002708 equals 2.708 times 10 to the minus 3. And of course this is 3 and it's minus 3 because we've shifted the decimal point 3 places to the right. And now for our next exercise. This will be on trigonometric ratios. We have a right-angled triangle and we have the three trigonometric functions displayed on the screen for reference. So the right-angled triangle, of course, has the angle theta, the right angle, the side adjacent to the angle theta, the side opposite to the angle theta, and the hypotenuse, which is opposite the right angle. So let's have a look at the first exercise. In this right-angled triangle shown, we are required to find the length of x to one decimal place. So we have the angle theta, we have one side given, and one side which we are required to find. So we are required to find the side opposite the angle. We have, or we know, the adjacent side, or the length of the adjacent side. So we're going to use the formula tan theta equals opposite over adjacent. So we have tan 25 degrees equals x over 3.5, which is the adjacent. And rearranging gives us x equals 3.5 times tan 25 degrees, which implies that x equals 1.6. Now let's have a go at review exercise 4b. We are required to find the length of x to one decimal place in the given diagram. We have the angle, which is 55 degrees, and we have the side opposite to it, which is 4 centimeters. And we are required to find the hypotenuse, x. So when solving this, we need to use the formula sin theta equals opposite over hypotenuse to give us sin 55 degrees equals 4, which is the opposite, over x, which is the hypotenuse. And rearranging this gives us x equals 4 over sine 55 degrees, which is x equals 4.9 centimeters. And now for exercise 5a, we are required to find the size of theta to 1 decimal place in the given diagram. So we have a right-angled triangle, we have an unknown angle, we have the side opposite to it, which is 1.5 centimeters, and we have the hypotenuse, which is 7 centimeters. So we're going to use the sine formula again. We have sine theta equals opposite over hypotenuse. And plugging in the values, of course theta is unknown, so we leave that as it is. We have the opposite, which is 1.5 centimeters, and the hypotenuse, which is 7 centimeters. And therefore theta equals sine inverse 1.5 over 7, which implies that theta equals 12.4 degrees. And now for review exercise 5b, we are required to find the size of theta to 1 decimal place in the given diagram. So in this diagram, we have the opposite, which is 2 centimeters, and we have the adjacent, which is 3.5 centimeters. And of course, we're required to find theta. Therefore, we use the formula tan theta equals opposite over adjacent. So here's our theta plugged in. Of course, that doesn't change because it's unknown. We have the opposite, which is 2 centimeters, and we have the adjacent, which is 3.5 centimeters. Therefore, theta equals tan inverse 2 over 3.5, which implies that theta equals 29.7 degrees. This brings us to the end of this session. If you have understood its contents, you should be able to factorize quadratic equations using the quadratic formula and otherwise. You should also be able to convert kilometers per hour to centimeters per second, and grams per centimeter cubed to kilograms per meter cubed. You should also be able to convert large and small numbers to standard form, and use trigonometry to find missing sides or angles. Thank you very much for listening.